Welcome, everyone. I'm excited to kick off our presentation today. Our first slide is titled, Metals and Nonmetals. Today, we'll explore the different properties and characteristics of metals and nonmetals. We'll look at how they differ, their uses, and why they are important in our daily lives. So, let's dive in and discover the fascinating world of elements. Let's explore some key topics related to metals and their properties. First, we'll look at the prevention of corrosion, which is essential to protect metals from deterioration over time. Then, we'll examine the steps involved in extracting metals from their ores, a crucial process in metallurgical engineering. Moving on, we'll discuss how metals and nonmetals react, highlighting the differences in their chemical behavior. Next, we'll touch on corrosion again, emphasizing its impact and how we can prevent it. We'll also consider the occurrence of metals in nature, which varies depending on their reactivity. The reactivity series of metals is fundamental because it helps us understand which metals are more reactive and how they behave in different reactions. After that, we'll look at the refining of metals, a vital step to obtain pure metals for various uses. Then, we'll cover the extraction of metals, focusing on methods used to isolate them from their ores. We'll also delve into ionic compounds, specifically electrovalent compounds, explaining how they form through electron transfer. Following that, we'll discuss the chemical properties of metals, including their tendencies to lose electrons and form positive ions. We'll look at the formation of sodium chloride, NaCl, as an example of a simple ionic compound. Finally, we'll review the physical properties of metals, such as conductivity, malleability, and luster, which make them useful in countless applications. Throughout this presentation, remember how these points connect to our overall theme of understanding metals' behavior, extraction, and applications. Let's take a closer look at the physical properties of metals. Metals are fascinating because they have several distinctive characteristics that make them useful in so many applications. For starters, they are generally good conductors of heat and electricity, which is why they are used in electrical wiring and cookware. Their ability to conduct heat efficiently means they can transfer energy quickly, making them ideal for heat exchangers as well. Another key property is their malleability and ductility. Malleability means they can be hammered or rolled into thin sheets without cracking, while ductility allows them to be stretched into wires. These properties are essential in manufacturing processes like shaping and forming metals into various components. Metals also tend to have a shiny, metallic luster, which is why they are often used decoratively. This shine results from their ability to reflect light effectively. Additionally, metals are generally dense and strong, providing durability and structural integrity in buildings, vehicles, and machinery. Understanding these physical properties helps us appreciate why metals are so versatile and widely used across industries. Their unique combination of conductivity, malleability, luster, and strength makes them fundamental materials in our daily lives and technological advancements. Metals are generally excellent conductors of heat, which means they can transfer heat quickly and efficiently. When we talk about the best conductors, silver and copper top the list, making them ideal for electrical wiring and thermal applications. On the other hand, lead and mercury are poor conductors, so they don't transfer heat as effectively. Metals are also malleable, meaning they can be hammered or beaten into thin sheets without breaking. This property is quite useful in manufacturing, allowing us to shape metals into various forms. Another key property is that metals are sonorous. When you strike a metal object, it produces a ringing sound, which is due to their ability to vibrate and produce sound waves. Metals generally have high boiling points, so they remain in the liquid state only at very high temperatures, which is important for processes like melting and casting. They also have a metallic luster, giving them that shiny appearance we often associate with jewelry and coins. This shine results from their ability to reflect light effectively. In addition, metals are good conductors of electricity. Silver and copper, again, are the top performers here, which makes metals essential in electrical and electronic industries. Most metals have high melting points, although there are exceptions. For example, gallium and cesium have low melting points and can melt in the palm of your hand, highlighting how some metals are quite unique. Metals are generally hard, providing durability and strength, but there are exceptions like lithium, potassium, and sodium, which are softer and more reactive. They are also ductile, meaning they can be drawn into wires without breaking, a property that is crucial for electrical wiring and other applications. Lastly, metals are solids at room temperature, except for mercury, which is liquid. This solid state at ambient conditions is fundamental to their structural uses and properties. Let's take a closer look at the physical properties of nonmetals. Firstly, nonmetals are generally poor conductors of heat, which means they don't transfer heat very well. This is an important characteristic because it affects how they are used in thermal insulation. Next, nonmetals are not malleable, so they can't be hammered or rolled into thin sheets like metals can. This makes them quite different in terms of physical flexibility. When we look at nonmetals that are solids and liquids, they tend to have low boiling points. This means they change from liquid or solid to gas quite easily at relatively low temperatures. Most nonmetals lack luster, or shine, with the exception of iodine crystals, which do have a shiny appearance. This lack of shine is another key visual difference from metals. Nonmetals are also not sonorous, meaning they don't produce sound when struck, unlike metals which are often sonorous. In terms of electrical conductivity, nonmetals are generally poor conductors of electricity. The notable exception here is graphite, which is a good conductor and is used in pencils and batteries. Additionally, nonmetals with solid or liquid states tend to have low melting points, so they melt easily at relatively low temperatures. Most nonmetals are soft, with the exception of diamond, which is actually the hardest natural substance known. This softness or hardness varies widely among different nonmetals. They are also not ductile, meaning they cannot be drawn into wires like metals can. Finally, nonmetals can be found in different states of matter: solids like carbon, sulfur, and phosphorus, liquids like bromine, and gases such as oxygen, hydrogen, and nitrogen. Recognizing these physical properties helps us understand their behavior and how they differ from metals, which is essential as we explore their chemical properties later on. Now let's take a closer look at the chemical properties of metals. Metals are fascinating because they have some unique chemical behaviors. For instance, they tend to lose electrons easily, which makes them good conductors of electricity and heat. This property is linked to their ability to form positive ions, or cations, during chemical reactions. Metals also tend to react with acids, releasing hydrogen gas in the process. This reactivity varies among different metals, with some, like sodium and potassium, being very reactive, while others, like gold and platinum, are much less so. Another important point is that metals often form compounds called oxides when they react with oxygen. These oxides can be basic, which means they can neutralize acids. Understanding these chemical properties helps us see why metals are so useful in everyday applications, from electrical wiring to catalytic converters. These behaviors are fundamental to how metals interact with their environment and other substances. Let's take a closer look at some reactions of aluminium oxide, or Al2O3. When it reacts with sodium hydroxide, NaOH, it forms sodium aluminate, NaAlO2, along with water. This reaction is considered acidic in nature. On the other hand, aluminium oxide also reacts with hydrochloric acid, HCl, to produce aluminium chloride, AlCl3, and water, and this reaction is classified as basic. Now, some metal oxides are interesting because they can behave as both acids and bases. They are called amphoteric oxides. For example, aluminium oxide and zinc oxide are amphoteric. You see this in actions like potassium oxide, K2O, reacting with water to form potassium hydroxide, KOH. Similarly, potassium reacts with oxygen to form potassium oxide, K2O, and sodium oxide, NuTWO, reacts with water to produce sodium hydroxide, NaOH. When sodium reacts with oxygen, it forms sodium oxide, NuTwo, and aluminium. When heated, reacts with oxygen to produce aluminium oxide, Al2O3. Some metal oxides are primarily basic because they react with water to form bases. For instance, when aluminium is heated, it combines with oxygen to form aluminium oxide, which is essential in many industrial processes. Copper also reacts with oxygen when heated to produce copper oxide, CuO. The overarching concept here is that metals tend to react with oxygen to form metal oxides, which can have different properties, some acidic, some basic, and some amphoteric, depending on the specific metal and conditions. This understanding helps us see the broad range of reactions metal elements can undergo with oxygen, shaping many materials and compounds we encounter in both nature and industry. Let's talk about how different metals react with oxygen. Some metals like magnesium, aluminum, zinc, and lead develop a protective oxide layer when they are exposed to oxygen. This layer acts like a shield, preventing further oxidation, and that's why we call these metals self-protecting. Now, if we look at copper, when it's heated, it doesn't catch fire or burn. Instead, it forms a black coating of copper oxide on its surface. It's a bit different from other metals in that way. Magnesium, on the other hand, is quite reactive. When you heat it, it burns with a bright, intense flame, so it reacts vigorously with oxygen. Silver and gold are special because they don't react with oxygen at all, even at very high temperatures. That's why they are so resistant to corrosion. If we take iron and heat it, it glows brightly, showing a strong reaction to heat, though it doesn't necessarily form a protective layer like some other metals. Finally, some metals like potassium and sodium are extremely reactive. They react vigorously with oxygen and can catch fire if left exposed. That's why we store them in kerosene, to prevent any accidental combustion. Understanding these reactions helps us see how different metals behave and why certain metals are more suitable for specific applications due to their reactivity with oxygen. Let's take a closer look at how different metals react with water. Metals like aluminium, iron, and zinc are somewhat cautious. They only react with steam, not liquid water, to form metal oxides and release hydrogen gas. Calcium, on the other hand, reacts less violently, but still actively, with water to produce calcium hydroxide and hydrogen. Now, some metals are quite inert when it comes to water. Lead, copper, silver, and gold do not react with water at all, which is why they are often used in jewelry and coins. Magnesium is interesting because it reacts only with hot water, forming magnesium hydroxide and hydrogen. And then we have the very reactive metals, sodium and potassium. They react violently with cold water, producing sodium hydroxide or potassium hydroxide and hydrogen, and they can catch fire in the process. The overall idea here is that the reactivity of metals with water varies significantly. For example, iron reacts with water to form iron oxide, aluminum forms aluminum oxide, calcium forms calcium hydroxide, and potassium and sodium produce their respective hydroxides along with hydrogen gas. So, in essence, metals react with water to form either metal oxides or hydroxides plus hydrogen. This variation in reactivity is key to understanding their behavior and uses in different applications. Let's take a closer look at how metals react with acids, starting with nitric acid. When copper reacts with nitric acid, the reaction produces copper nitrate, water, and nitrogen dioxide gas. What's interesting here is that hydrogen gas isn't released in this process. That's because nitric acid is a strong oxidizing agent. It actually oxidizes the hydrogen to water and gets reduced itself to nitrogen oxides. This is a key point to remember because it differentiates nitric acid from other acids in reactions with metals. Now, moving on to metals like copper, silver, and gold. These metals don't react with dilute hydrochloric acid at all. Their reactivity is quite low, which means they don't easily form salts or release hydrogen in these reactions. Speaking of reactivity, It's important to understand that metals react with dilute acids in different ways depending on their position in the reactivity series. The general trend is that magnesium is the most reactive among these, followed by aluminum, zinc, and then iron. For example, when iron reacts with dilute hydrochloric acid, it forms iron chloride and releases hydrogen gas. Zinc reacts similarly, forming zinc chloride and hydrogen. Aluminum also reacts to produce aluminum chloride and hydrogen gas, though the reaction is a bit more involved due to aluminum's reactivity. And magnesium. It reacts with dilute hydrochloric acid to produce magnesium chloride and hydrogen gas as well. So the key takeaway here is that metals react with dilute acids to produce salts and hydrogen gas, but the ease and speed of these reactions depend heavily on the metal's reactivity. This variation is crucial to understanding how different metals behave in chemical reactions, especially in industrial and laboratory contexts. Now, after about 15 to 20 minutes, you'll notice some interesting changes happening in the solutions. For example, when iron reacts with copper sulfate, the reaction produces iron sulfate and solid copper. This shows that iron displaces copper from its salt solution. Similarly, zinc can also displace copper from copper sulfate, forming zinc sulfate and copper metal. The same goes for magnesium. When magnesium reacts with copper sulfate, it produces magnesium sulfate and copper. The key idea here is that a more reactive metal can displace a less reactive metal from its salt solution. This process is known as a displacement reaction. It's a fundamental concept in understanding how metals interact with different salt solutions. So, in essence, when you have a metal that's more reactive, it will push out the less reactive metal from its compound, leading to these observable changes in the solutions. This principle helps us predict and understand many reactions in chemistry involving metals and salts. Let's take a closer look at the reactivity series of metals. This is a list that ranks metals based on how easily they react with other substances, like acids or water. The most reactive metals are at the top, while the least reactive are at the bottom. Understanding this series helps us predict how different metals will behave in chemical reactions. For example, metals like potassium and sodium are very reactive, so they react quickly with water, sometimes explosively. On the other hand, metals like gold and platinum are very unreactive and won't react easily at all. This series is crucial because it explains why some metals are used in certain applications, and also why some metals can be extracted from ores more easily than others. Overall, the reactivity series is a fundamental concept that ties into the broader theme of how metals behave chemically. Let's take a closer look at the reactivity series of metals. Starting from the least reactive, we have O, which is gold. Gold is very stable and doesn't react easily. Next is Ag, or silver, which is slightly more reactive but still quite resistant to corrosion. Mercury, or Hg, is unique because it's a liquid at room temperature, and its reactivity is moderate. Moving on, copper, or Cu, is more reactive than silver and gold but still fairly stable. Hydrogen, represented by H, is important because it helps us compare metals' reactivity with acids. Lead, or Pb, comes next, showing more reactivity than copper. Iron, or Fe, is quite reactive and easily forms compounds with oxygen. Zinc, or Zn, follows, and it's interesting to note that as we go down the series, the reactivity decreases. Aluminum, magnesium, calcium, sodium, and potassium follow in order, with potassium being the most reactive in this list. The key concept here is that arranging these metals in order of decreasing reactivity is called the reactivity series of metals. This series is crucial because it helps us predict how metals will react in different chemical reactions and is fundamental in understanding corrosion, displacement reactions, and more. So, the reactivity series is essentially a ranking that helps us understand the behavior of metals in various chemical processes. So now let's talk about how metals and nonmetals react. Metals tend to lose electrons when they react, which means they form positive ions, or cations. This is because they have relatively low ionization energies, making it easier for them to give up electrons. On the other hand, nonmetals usually gain electrons during reactions, forming negative ions or anions since they have higher electronegativities. This difference in behavior is fundamental to understanding chemical reactions. Metals often react with nonmetals to form compounds called ionic compounds, where electrons are transferred from the metal to the nonmetal. For example, sodium reacting with chlorine to produce sodium chloride. It's also interesting to note that the reactivity of metals varies across the periodic table. Alkali metals like sodium and potassium are very reactive, while noble metals like gold are much less so. For nonmetals, reactivity depends on their ability to gain electrons, which is strongest in elements like fluorine. Overall, recognizing these reaction patterns helps us predict how different elements will behave and interact, which is key to understanding chemical reactions in everyday life and industrial processes. Let's take a closer look at how metals like magnesium and sodium tend to lose electrons during chemical reactions. For magnesium, the reaction involves losing 2 electrons to form Mg2. Its electronic configuration is 2-8-2, which means it has 2 electrons in its outermost shell. When it loses those 2 electrons, it becomes a stable Mg2 ion. Similarly, sodium loses 1 electron to become Na+. Its electronic configuration is 2-8-1, with just a single electron in its outermost shell. Losing that 1 electron makes it a stable Na+ ion. This process of losing electrons and forming positive ions is characteristic of metals, and because they tend to give up electrons easily, we call them electropositive elements. They are reactive and tend to form positive ions in chemical reactions, which is a fundamental concept in understanding their behavior in the periodic table. Let's take a closer look at how nonmetals tend to gain electrons and form negative ions. Starting with oxygen, it gains 2 electrons to become. You'll notice the electron configuration changes from 2-6 to 2-8, which is a more stable octet configuration. This process is essential because it highlights oxygen's high electronegativity and its tendency to attract electrons. Similarly, chlorine gains 1 electron to become Cl-. Its electron configuration shifts from 2-8-7 to 2-8-8, completing its outer shell. Chlorine's electron affinity and electronegativity make it very eager to accept electrons, which is why it's called an electronegative element. Overall, nonmetals like oxygen and chlorine gain electrons, forming negatively charged ions, known as anions. This behavior is a key part of their chemical nature and explains their role in forming ionic compounds. Remember, their electronegativity drives this electron gain, making them essential players in various chemical reactions. Let's take a closer look at how a sodium chloride molecule, or NaCl, is formed. This process really highlights the fundamental concept of ionic bonding. Sodium, which is a metal, has 1 electron in its outermost shell that it wants to get rid of to become more stable. Chlorine, on the other hand, is a nonmetal with 7 electrons in its outer shell and needs 1 more to complete it. When these 2 elements come together, the sodium atom donates that 1 electron to the chlorine atom. This transfer results in the sodium atom becoming a positively charged ion, or cation, and the chlorine atom becoming a negatively charged ion, or anion. These opposite charges create an electrostatic attraction, which is the key force holding them together in the ionic bond. The result is the formation of sodium chloride, a stable compound commonly known as table salt. This process exemplifies how elements interact to form compounds through electron transfer and electrostatic forces, which is a central theme in understanding chemical bonding. Let's start by looking at sodium, or Na. Its atomic number is 11, which means it has 11 protons in its nucleus. Its electronic configuration is 2-8-1, so it has 2 electrons in the first shell, 8 in the second, and 1 in the outermost shell. That single valence electron is quite important because sodium tends to lose it to achieve a stable electron configuration. When sodium loses that 1 valence electron, it forms a positively charged ion, Na+. Now turning to chlorine, or Cl. Its atomic number is 17, with an electronic configuration of 2-8-7. That means it has 7 electrons in its outermost shell, making it 1 electron short of a full octet. To become more stable, chlorine gains 1 electron, forming a negatively charged ion, Cl-. When sodium loses its valence electron and chlorine gains 1, these oppositely charged ions are attracted to each other due to electrostatic forces. This attraction results in the formation of an ionic bond, creating sodium chloride, or NaCl. So, in essence, the key points here are that sodium and chlorine interact through electron transfer, sodium giving up 1 electron and chlorine gaining 1, and this transfer leads to the formation of ions that bond together to form NaCl. This process beautifully illustrates how atoms attain stability through ionic bonding, which is a fundamental concept in understanding chemical compounds and their structures. Let's talk about ionic compounds, also known as electrovalent compounds. These are a special type of chemical compound formed through the transfer of electrons. When a metal reacts with a nonmetal, the metal tends to lose electrons and become a positively charged ion, called a cation. Conversely, the nonmetal gains those electrons and becomes a negatively charged ion, or an anion. This transfer creates an electrostatic attraction between the oppositely charged ions, which is the fundamental force holding the compound together. This electrostatic attraction results in the formation of a stable, crystalline structure. Ionic compounds tend to have high melting and boiling points because a lot of energy is needed to break those strong electrostatic forces. They also tend to be soluble in water, and when dissolved, they conduct electricity due to the movement of free ions in solution. Understanding ionic compounds is crucial because they play a key role in many physical and chemical processes, from biological functions to industrial applications. They exemplify how the transfer of electrons leads to the formation of stable, often vital, chemical substances. Ionic compounds are formed when electrons are transferred from a metal to a nonmetal. This transfer of electrons is what creates the ionic bond that holds the compound together. Essentially, the metal loses electrons and becomes a positively charged ion, or cation, while the nonmetal gains those electrons and becomes a negatively charged ion, or anion. This transfer is key because it explains how ionic compounds are structured and why they have their characteristic properties, like high melting points and electrical conductivity when molten or dissolved. Understanding this electron transfer helps us see the bigger picture of how elements combine to form stable compounds in nature. Now, let's talk about some key properties of ionic compounds. First, they conduct electricity when in a molten state or when dissolved in water. This is because, in these conditions, the ions are free to move around, allowing electric current to pass through. Second, ionic compounds are soluble in water, but generally insoluble in organic solvents like petrol or kerosene. This difference in solubility is due to the strong ionic bonds that water can weaken, but organic solvents cannot. Third, they are crystalline solids, which means they form a regular, repeating pattern of ions. This crystal structure gives them their characteristic shape and stability. Fourth, ionic compounds tend to have high melting and boiling points. Because of the strong electrostatic forces between the ions, a lot of energy is needed to break these bonds and change their state. Lastly, these compounds are formed through the transfer of electrons, resulting in ions, positively charged and negatively charged particles that are held together by electrostatic attraction. Understanding these properties helps us see how ionic compounds behave and why they are so important in various chemical and industrial applications. Now, let's take a closer look at the occurrence of metals. As we can see here, metals are found in various environments around the world. Their distribution is not random, but influenced by geological processes that concentrate them in specific areas. This slide highlights some of the key points about where and how metals occur naturally. Understanding these patterns is crucial because it guides exploration and extraction efforts. It also connects to the overall theme of resource availability and sustainable management. Recognizing where metals are naturally found helps us better appreciate the importance of responsible mining and the potential for discovering new deposits. So, keep in mind that the occurrence of metals is a fundamental aspect that underpins their economic and technological significance. Some metals, like gold, silver, and platinum, are actually found in the free state in the Earth's crust. This happens because they are the least reactive metals. Unlike other metals that tend to combine with other elements and form compounds, these metals remain in their pure, metallic form naturally. This is a key point because it highlights how reactivity influences the form in which metals are found. Understanding this helps us grasp the broader picture of metal extraction and their natural occurrence in the Earth. So, in summary, these metals are unique because their low reactivity allows them to be found freely, making them easier to extract in their pure form. Let's start by understanding what gangue is. Gangue refers to the impurities that are present in the ore. These impurities can be rock particles, sand particles, clay particles, and so on. They are basically unwanted materials mixed with the valuable ore. Now, moving on to ore itself. An ore is essentially a mineral from which we can extract metals profitably. It's not just any mineral, but one that contains enough of the desired metal to make its extraction economically feasible. Finally, let's talk about minerals. Minerals are elements or compounds that occur naturally inside the Earth's crust. They form the building blocks of rocks and ores. Connecting these points to our overall theme, understanding what constitutes ore and gangue is crucial because separating the valuable minerals from impurities is a key step in the extraction process. The better we understand these components, the more efficient our metallurgical processes become. Let's talk about the main steps involved in extracting metals from their ores. First, we have the concentration of the ore, which is all about removing the gangue, or impurities, from the ore. This step is crucial because it makes the extraction process more efficient. Once we have a concentrated ore, the next step is reduction to the metal itself. This involves chemical processes that convert the concentrated ore into pure metal. Finally, we move on to refining, which is all about purifying the metal to achieve the desired quality. These three steps, concentration, reduction, and refining, form the backbone of how we extract metals from their ores, connecting directly to the overall theme of efficient and effective metal extraction methods. Now, let's take a closer look at the steps involved in extracting metals from their ores. First, the process begins with mining, where we locate and extract the ore from the earth. This is a crucial step because the quality and quantity of the ore directly impact the efficiency of the entire process. Next, the ore is crushed and ground into smaller pieces to increase the surface area, making it easier to process. This preparation is vital for the subsequent steps, as it helps in the efficient separation of the metal from other materials. The third step involves concentration or beneficiation where impurities are removed through processes like froth flotation or magnetic separation. This step enhances the purity of the ore, ensuring that we get a higher yield of the desired metal. Following concentration, we move to extraction. Here, the concentrated ore undergoes chemical or thermal treatments, such as roasting or reduction, to extract the metal. For example, in smelting, the ore is heated with a reducing agent to obtain the metal in its molten form. Finally, the extracted metal is refined to achieve the desired purity and quality. This can involve electrolysis or other refining techniques, depending on the metal. All these steps are interconnected and essential for efficiently turning raw ore into usable metal, which is fundamental to many industries and our overall economy. Understanding this process highlights the importance of each stage in ensuring we get the most out of our natural resources. Now, let's look at the refining process involved in extracting metals from their ores. Once we've reduced the ore to metal, the next step is refining to obtain pure metal. This process varies depending on how reactive the metal is. For metals of low reactivity, we typically use roasting. Roasting involves heating the ore in the presence of air to convert sulfides or other compounds into oxides, making the metal easier to extract. For metals of medium reactivity, the common methods include calcination for carbonate ores and roasting for sulfide ores, which help in breaking down the ore and preparing it for further purification. When it comes to metals of high reactivity, electrolysis of molten ore is the primary method. This process uses electrical energy to break down the ore directly into pure metal and other components. Overall, the extraction process is tailored to the reactivity of the metal, ensuring efficiency and purity in obtaining the final metal product. Let's talk about the extraction of metals. This process is a crucial part of how we obtain the materials we use every day. First, we start with ores, which are naturally occurring solid materials that contain enough of a metal to make extraction worthwhile. The goal is to isolate the metal from other elements in the ore. One common method is smelting, where the ore is heated to high temperatures in a furnace. This causes chemical reactions that separate the metal from impurities. Sometimes, we use reduction, which involves adding a substance like carbon to help remove oxygen from metal oxides, turning them into pure metal. It's important to highlight that extraction methods vary depending on the type of metal and the ore's composition. For example, metals like aluminum require complex processes like electrolysis, while others like iron can be extracted more straightforwardly through smelting. Understanding these extraction methods connects to the bigger picture of resource management and environmental impact. Some processes are energy-intensive and can have significant environmental footprints, so advancements in extraction technology aim to make these processes more sustainable. Overall, the extraction of metals is a fascinating combination of chemistry and engineering, enabling us to access the essential materials that drive industry and innovation. Now let's look at an example. Mercury is obtained from its ore, cinnabar, which has the chemical formula. The process involves heating cinnabar in the presence of oxygen, which helps release the mercury. Moving on to a more general concept, metals that are low in the activity series can be reduced to their metallic form through a process called roasting. Essentially, roasting involves heating these metals in the presence of oxygen. This process is particularly important because these low-activity metals don't easily react with other substances at room temperature. But through roasting, we can extract them efficiently. Understanding which metals can be reduced this way helps us grasp how different extraction methods are tailored to the properties of each metal, fitting into the broader theme of how we obtain and refine metals from their ores. Non-oxide ores can be converted into their oxide form through processes like roasting or calcination. These are important methods in metallurgy that help us extract metals more easily. Metals such as zinc, iron, and lead are often found in nature not just as pure elements, but as compounds like oxides, sulfides, or carbonates. Recognizing these forms is crucial because it influences how we process and extract the metals. Also, it's interesting to note that these metals tend to be located in the middle of the activity series. This positioning tells us that they are more reactive than some metals, but less reactive than others, which affects the methods we use for their extraction. Understanding this helps us optimize our processes and improve efficiency. Overall, these points highlight how the form in which a metal ore occurs and its position in the activity series are key factors in metallurgical processing. Sometimes, reactive metals like sodium, calcium, and aluminum are used as reducing agents to extract metals from their oxides. These metals are quite reactive, which makes them effective in driving the reduction process. One interesting example of this is thermit reactions. In thermit reactions, a highly reactive metal reduces a metal oxide, releasing a lot of heat and energy in the process. This technique is particularly useful for welding and metal recovery because it produces very high temperatures. So, in essence, thermit reactions are a practical application of using reactive metals as reducing agents to obtain pure metals efficiently. Now, let's talk about metals that are at the top of the activity series, such as potassium, sodium, calcium, and aluminum. These metals are so reactive that you can't simply obtain them by heating their ores. Instead, we use a different method, electrolytic reduction of their molten chlorides. This process is essential because their high reactivity makes traditional extraction methods ineffective. By passing an electric current through their molten chlorides, we can effectively reduce these metals to their metallic form. This highlights the importance of understanding the activity series, as it guides us on the best extraction techniques for different metals. Now, let's talk about refining of metals, which is a crucial step in making metals suitable for various applications. This process helps us remove impurities that can weaken the metal or affect its performance. Refining ensures that the final product has the desired purity and quality. There are different methods of refining, such as electrolytic refining, which uses electrical currents to purify metals like copper and gold. Another common method is refining through chemical processes, where specific chemicals are used to extract impurities. This step is important because it directly impacts the durability, strength, and overall usefulness of the metal in industries like construction, manufacturing, and technology. Remember, refining isn't just about cleanliness. It's about achieving the precise qualities needed for specific uses, which ties back to our overall theme of optimizing metal properties for different applications. Let's look at an example to understand this better. In the electrolytic refining of copper, for instance, a block of impure copper is used as the anode, while a thin sheet of pure copper acts as the cathode. When an electric current passes through, impurities are removed from the impure copper, and pure copper is deposited onto the cathode. This process is actually the most common method used for refining metals. The main goal here is to remove impurities, which are unwanted substances, to obtain pure, high-quality metal. This process of removing impurities to get the pure metal is what we call refining of metals. So, overall, refining is essential for ensuring the metal's purity, which is crucial for its proper use in various applications. Let's talk about corrosion. Corrosion is essentially the deterioration of materials, usually metals, due to chemical reactions with their environment. It's a natural process, but it can lead to serious problems like structural failures and costly repairs. When metals like iron or steel are exposed to moisture and oxygen, they form rust, which weakens the material over time. Understanding corrosion is crucial because it impacts the longevity and safety of our structures and equipment. By managing corrosion effectively, we can extend the lifespan of materials and reduce maintenance costs. It ties into the overall theme of material durability and proper maintenance strategies, reminding us why preventing corrosion is so vital in our field. Let's look at an example to understand corrosion better. Imagine a piece of iron developing a brown coating of rust on its surface. This is a classic illustration of corrosion in action. Corrosion, in simple terms, is the damage that occurs when metals react with elements like oxygen, moisture, or carbon dioxide. These reactions gradually weaken the metal over time. So whenever you see that brown, flaky layer on iron or steel, you're witnessing corrosion. It's important to recognize that corrosion isn't just surface level. It can compromise the structural integrity of metal objects if left unchecked. This concept ties into our overall discussion about material durability and the importance of protective measures in engineering and everyday life. Now, let's look at the setup for our experiment. Test tube 3 contains plain water, which is essential for rusting since moisture is a key factor. Test tube 2 has boiled distilled water with a layer of oil poured over it. The oil acts as a barrier to air, preventing oxygen from reaching the water. And finally, test tube 1 contains anhydrous calcium chloride, which is a drying agent that absorbs moisture from the air. The purpose of this experiment is to demonstrate that both air and moisture are necessary for rusting to occur. By comparing what happens in each test tube, we can see clearly how these elements influence the rusting process. This ties into our overall theme of understanding the conditions needed for corrosion, highlighting why environments with moisture and oxygen accelerate rust formation. Let's talk about prevention of corrosion. Corrosion can cause significant damage to metal structures and equipment, so preventing it is crucial for safety and longevity. One of the most effective methods is applying protective coatings, like paint or specialized coatings, which act as a barrier against moisture and oxygen. Another key point is cathodic protection, where we use sacrificial anodes or impressed current systems to protect the metal from corroding. Regular maintenance and inspections are also vital. Catching early signs of corrosion allows us to act before it causes serious damage. Additionally, controlling environmental factors, such as reducing humidity or using dehumidifiers in enclosed spaces, can make a big difference. These prevention strategies are essential not just for extending the life of equipment, but also for ensuring safety and reducing costs over time. Overall, by implementing these measures, we can significantly mitigate corrosion and maintain the integrity of our structures. Now, let's look at some of the common methods used to prevent corrosion of metals. One effective way is alloying, which involves making alloys. By combining metals, we can enhance their resistance to corrosion. For example, steel is an alloy that's much more durable. Next, we have tinning, which is coating a metal with a layer of tin. This is often done to protect metals like iron from rusting, especially in food packaging and electronics. Applying paint also creates a protective barrier on the surface of the metal, shielding it from moisture and oxygen, which are key factors in corrosion. Another method is electroplating, where we coat a less reactive metal, such as chromium, with a thin layer of a more resistant metal. This not only improves appearance, but also provides corrosion resistance. Galvanization is a popular technique where we coat steel or iron with zinc. Zinc acts as a protective barrier, preventing the underlying metal from coming into contact with the environment. Lastly, applying oil or grease is a simple but effective way to protect metals, especially in machinery, by creating a barrier that repels moisture and reduces friction. All these methods are part of a broader strategy to prevent corrosion, which is essential to prolong the life and maintain the integrity of metal structures and objects. Now let's look at some common examples of alloys. Steel, for instance, is primarily made of iron and carbon, which gives it strength and durability. Stainless steel adds elements like cobalt and nickel to improve corrosion resistance, making it ideal for kitchen utensils and medical instruments. Brass is an alloy of copper and zinc, often used in musical instruments and decorative items. Bronze combines copper and tin, historically important for tools, sculptures, and coins. Solder, which typically contains lead and tin, is used for welding electrical wires and creating strong, conductive joints. An interesting point to remember is that if an alloy contains mercury, it's called an amalgam. These are often used in dental fillings or other specialized applications. Overall, alloys are crucial because they enhance the properties of pure metals, making them more suitable for specific uses. They are a key part of engineering, manufacturing, and everyday life, demonstrating how combining metals can lead to better, more versatile materials.